Welcome back. In this video, we are going to finish chapter 3 with mentioning some more general versions of the mean value theorem. Okay, so let us recall version 3.0 that you proved earlier, which was the key to proving the other versions. Okay, we proved in version 3.0 that it's a particular case, actually, of version 3.3. If we consider a map defined on a closed interval AB of R and that takes values in a norm space, which is continuous on the closed interval AB and differentiable inside. Okay. So if the derivative is bounded by a constant m for all x inside AB, then f of b minus f of a is less than this constant times b minus a. Okay. So we proved that, and the proof was not easy, actually. But this was the key to proving later versions. Okay, now we can extend this result. Okay, so for this, observe that this is actually a particular case of a more general theorem. If we set g of x equal m times x, so this is just actually a function of one real variable, x is actually in AB, then the derivative is just m, and mb minus a, just the difference between g of b and g of a. Okay, so this version that we prove is actually a particular case of this more general version. If we have two maps, both defined on a closed interval AB of R, but f takes values in a norm space and g takes values in R. Okay, both being continuous on the closed interval AB. We need continuity on the whole interval, on the closed interval, because we have to write g of b minus g of a. So if you don't assume continuity, the result is wrong, actually. But we don't need differentiability at a and b, or left and right differentiability at a and b. So we just need differentiability inside. Okay, so if the norm of the derivative of f is less or equal than the derivative of g, because now this is a real number, and this assumes that, this implies actually that g prime is non-negative. Okay, so in particular, g is increasing or non-decreasing. So if the derivative of f norm is bounded by the derivative of g, then the norm of f of b minus f of a is less or equal than g of b minus g of a. Okay, so this is a more general version of, so we'll call it version 3.4. Now, the proof is not more difficult, actually, because you can do it if you like. If you are interested, you just have to go to the proof of version 3.0 and modify it a little bit in order to get this more general result. Okay, so same proof, actually. But you can still push further, actually. We don't need to assume differentiability. We just have to assume right differentiability, not left differentiability, right. Okay, there's an error. Have to, okay. So, as you probably know, a function from an interval AB into f is said to be right Frechet differentiable at the point x0 if this one-sided limit exists. Okay, so assume here h is positive. So this is, we approach x0 from the right, so from above, if you like. So this is the right differentiability. Okay, and everything is real. Here h is real. Okay, so we cannot do the same definition if for maps defined on a normal space. Okay, this is really something particular to the real line, because we have the notion of left and right. And if this limit exists, in English it's denoted by fr prime of x0, derivative from the right. In French, f prime d, droite, dérivé à droite. Okay. And of course, we have a similar definition for left differentiability. So here, a more general, still more general version, we assume that, so same assumptions, but instead of differentiability, we assume only right differentiability. Okay. And the assumption is that the norm of the right derivative of f is less than the norm of the right derivative of g, and then the conclusion is the same. So here, if you you can, it's not, the proof is not, it's the same as the proof of theorem 3.0. Just go back to the definition actually. Okay, so the same proof works actually. And we can still push further. We don't need to assume right differentiability everywhere. It's enough to assume a right differentiability except at the countable set. Okay, so this will be the last theorem. The proof, of course, you can find it in the book of Cartan. So this is the last version. So same assumptions, but instead of right differentiability on the semi-closed interval AB, it's enough to assume right differentiability except at the countable set D. Okay, and the same inequality holds for all x not in D. Then the same conclusion holds. Okay, so we have to modify a little bit the proof of the previous version. Okay, because you have just to add an extra term taking into account this countable set D. Okay, now since I'm not going to use it in this generality, I will not prove it. The proof is in the book of Cartan. And by the way, to be honest, I never had to use this mean value theorem in this generality actually. So if you encounter an application, an interesting application of this general result, let me know so I can include it in later videos. But honestly, I never had to use that. Okay, so this concludes this short video and concludes chapter 3. So thank you for your attention. And in the next video, we are going to start with chapter 4 about higher order derivatives.